Hello everyone, my name is Chen Renjie. Today I want to talk about the boron diffusion of cobalt-boron-based magnetism film with different thickness and annealing temperature. We started by anomalous X-ray scattering and the neutron reflectivity. In the society of MRAN, the MTT structure has a great influence on the TMI ratio. To have a better TMI ratio, we need to coherent growth the cobalt-iron-2 crystalline phase on MgO layer. And to achieve this goal, originally we used cobalt-iron layer, but we replace the cobalt-iron with the cobalt-iron-boron. With the boron add-in, it will have a better and smoother interface, so it will have a better TMI ratio. But we still need to grow the cobalt-iron-2, so the boron need to take out by the annealing process. Once the annealing process, the boron may be diffused out to the interface in between the cobalt and the MgO layer, so will cause the magnetic dead layer. This will reduce the performance of the device. So in order to prevent this problem, we use the capping layer to prevent this problem. And in this work, we use the zirconium and the tantalum. The tantalum capping layer is being used in most of the research and the industry application. But from the theoretical prediction, it shows that the zirconium has a lower formation entropy, which means it will be much better to form the boron to prevent the magnetic dead layer. On the sample preparation, we use the magnetic sputtering to prepare the cobalt-iron-boron with 20-60-20 on the single crystal MgO01 substrate. And we use 3 different annealing temperatures in the vacuum environment. And we prepare 2 different thicknesses is because on the neutron experiment we did on the N-stove, it requires a thicker film to obtain a better SN ratio. And from the result and discussion, we can see the X-ray part that we use the SRD to observe the cobalt-iron-2 phase after annealing process. And the anomalous X-ray scattering basically is we focus on one peak and go through the different energy when close to the absorption kh of iron and cobalt itself. And from the neutron experiment, we can see that there are 2 curves. It is because when we do the experiment, we apply the magnetic field about 1 Tesla to make the magnetic saturate. And once these 2 curves be split out, that means the magnetic moment is higher. So after we fit in these 2 curves, we can have the scattering length density. We can separate to magnetic part and normal part and the imaginary part. Like magnetic scattering length density, we can use to explain the magnetic moment. And the imaginary part of the scattering length density, it can be used to explain the boron distribution of the whole field. On our conclusion, we can find out the SRD provide the data that the cobalt-iron-2 can be observed. And from the zirconium capping case, annealing at 500 degrees C may have a higher crystalline phase compared to the tantalum capping one. So which means the zirconium may be better to absorb boron. And from the anomalous result that we can see the difference of the cobalt and iron absorption itself. The ratio is almost close to 1:1 rather than iron 3 and cobalt 1. So which means the atomic concentration of this film after annealing may be 1:1. And the neutron result, we give a much more complicated model because we fit the result to know the magnetic moment contribution layer by layer. So from the SLD result, the magnetic contribution of the crystalline cobalt iron is higher than the cobalt iron boron after annealing, which means we can see this model after annealing is separate to 2 layers. And from this cobalt iron layer, you will have a higher magnetic moment. And the imaginary scattering density is mainly contribution of the boron because it is have a higher absorption cross-section compared to cobalt and iron itself. And we can observe the boron distribution from this result. And we can see that the zirconium is really have a higher imaginary part of the scattering length density. And also from the magnetic result, we can see that after annealing zirconium itself may have a higher magnetic moment on the cobalt iron layer. So this is our fitting model till now, and thank you for your listening.